move that one to answered. Okay, so another question I had. Okay, good. To answer it. It's from Victoria on number 5. Okay, and Griffin, it looks like you sent me one. Awesome. Number 9. I'm gonna just do like a quick sketch of these graphs so that we have it. For number 9. 4. So your first graph, and I don't think these iterated. I think these were the same for everybody. And I had a couple people ask me about this one also. So there's this, there's that. Something like this. And this point is the square root of 3, 0. This one is negative root 3, 0. This is the graph of f prime. And your other graph, of course, is going to be quadratic because this one was cubic. So I'm going down to about negative 12. And then it's going up through, obviously this is not to scale, 1 and negative 1. Actually, I really like these questions, but I can see why, I see why they're so good conceptually, which is why I like them. So it's f double prime. Okay, so you were asked a series of questions based off of these two graphs. The first one was find the critical numbers of f. Now remember, your critical numbers are places where your first derivative would be equal to 0. That's how you found them. Now, the graph of your first derivative is right here. So what you're looking for are places where the graph of your first derivative is 0, and that's going to give you the critical numbers of your original function f. So there's so much information that we can glean without even having the actual graph of f. So I'm going to say that here at this x-intercept at negative square root 3, and here at this one at 0, and over here at the square root of 3, I have x-intercepts on the f prime graph. So this is where f prime of x equals 0. Remember, a function is going to equal 0 at its x-intercepts. So these would be the critical numbers. And you just enter them as such, just x equals these values. Now, f is going to be increasing. WebAssign's driving me nuts with this. Anywhere your derivative is positive, and it's going to be decreasing anywhere your derivative is negative. So what you're looking for on these graphs is that your derivative is positive anywhere your function lies above the x-axis. So in this piece right here, from negative root 3 to 0, your graph lies above the x-axis. So this would be a portion where f is increasing, because we know that f is increasing when f prime of x is positive. And that's what we did with the first derivative test. We looked at the sign on an interval at a test point, and we said, okay, well, if the first derivative is positive, it must be the case that f is increasing. And that's what we're doing here, just looking at this graphically. So f prime of x is positive when the y values are positive. And that occurs from negative square root 3 all the way up to 0. So here we're just looking at the x values as we go through this interval. And then at 0, it starts to go down again. So we know it's going to be, f is going to be decreasing in between 0 and the square root of 3. But once I get beyond the square root of 3, the function is going to again be increasing. So from the square root of 3 up to infinity, I'm going to have f increasing because f prime is positive there. Now, this part C, I think, is asking you for decreasing. So same idea. We're going to say that f is decreasing when f prime of x is negative. And what you're looking for there are negative y values. So f prime is negative, meaning its y values are below the x-axis. And that happens to the left of the negative square root of 3. So all the way from negative infinity up to the negative square root of 3, your graph has these negative y values. And then we're seeing that same behavior from 0 all the way up to the square root of 3. And note that this covers your entire domain. You went from negative infinity to the negative square root of 3, and then picked it back up again up to 0, picked that back up again from 0 to the square root of 3, and then that went up from the square root of 3 to infinity. So everything's covered, and that's one nice thing to double check there. If you guys have questions as I'm going through this, please feel free to ask. D, at what numbers x, if any, does f have a local minimum? Hold on. All right. Children in stereo. All right, so the question was, at what numbers x does f have a local minimum? Okay. So you can do this in a couple different ways, but if I were you, I would be looking at my graph and looking at also my intervals. So I know that f is going to have a local minimum when my graph goes from decreasing to increasing. Kind of visualizing this, I'm looking for something like this to happen. The graph went from decreasing on the left and then increasing on the right. And what I'm seeing there is that I was decreasing on the interval from negative infinity to negative square root 3, but then I started to increase from negative square root 3 to 0. So it must be the case that I have a local min at that critical number. So I went from decreasing to increasing at the square root of 3. And then I also went from decreasing to increasing. Let's see, I was decreasing on 0 to the square root of 3, and then I started increasing again at the square root of 3, infinity. So I would say that the square, sorry, this was supposed to be negative, but it will also apply to positive. Plus or minus the square root of 3 basically are the two places where I went from decreasing to increasing. But you could also look at that on your graph as I went from negative to positive, and negative to positive. Now, you'll notice that at the critical number at 0, sorry, I never labeled that, but it looks pretty clear that it's the origin. I went from positive to negative. So in that case, we're going to have a local max. And I believe that's what E is asking. At what numbers does F have a local max? And again, I'm looking for a situation where I go from increasing to decreasing, or that my derivative is positive and then negative, and that's going to happen at x equals 0. And then F, where is F concave up? So for that, you're going to look at your graph for the second derivative. So f is concave up, and this is going to happen when f double prime is positive. F double prime is positive when its y values are above the x-axis, and that is going to happen here and here. These are the positive values for f double prime. So I would say that that happens from negative infinity up to -1, and then from 1 to infinity. G is, where is f concave down? And this happens when f double prime is negative, and f double prime is negative down here. All these y values are negative, so that happens between -1 and 1. And then the last one is list any inflection points, and it just wants the x values. Well, remember, inflection points are not only values that make your second derivative 0, but it must be the case that the concavity changes at those points. And note that in this case, your concavity went from up to down at -1, and it went from down to up at +1. So you would say that both x equals -1 and x equals +1 would be points of inflection on your graph. You can also see that they're x-intercepts of your graph. So those are places where f double prime of x is equal to 0, which is what you're looking for when you're looking for points of inflection. But it is indeed the case that the concavity changed from negative to positive or vice versa at those points. So there was a lot to unpack there, but I think it's really, it was a good question. Those are all good questions to go over, kind of test what you know graphically. All right, and that was it for my WebAssign questions. I spent like an hour and a half while my kids ate lunch today answering email questions, so I can see that we're in the weeds here. Anything else from the homework that was bugging you? Don't ask about number 7. That I emailed you about it. If you did it, you'll get extra points for it. But I don't really have the class time to spend on the algebra portion of that. Sorry, not that I wouldn't find it fun, but not in the cards for today. Wonderful. Well then, I had one thing I didn't get to talk about at the end of 4.4 yesterday. It's pretty short. It's just one theorem with an example attached to it. But I don't want to skip it because it is kind of important. Even though you won't use it a ton, you will see it again. So I want to talk about that real quick, and then we'll do some curve sketching. Maybe we'll post these. You know what I'm going to do is when I post the office hour notes from today, I'm going to post everything I just did in the office hour. And I went through number 5, which took like 3 pages. And then I'm even going to, I saved the notes. I started recycling them, the ones that I was doing at lunchtime. And then I decided I might as well hold on to them and scan them and upload those too. So I'm going to add these to that stack. And before I head downstairs tonight, I will scan all of it somewhere. Oh, here it is. This is what I did at lunch. You guys and your questions. I certainly don't mind answering them. It's just a little hefty today. See if I can organize them better. Some of them weren't totally complete. Maybe somebody asked me about a part that just like one part instead of all the parts. All right, so I'm going to upload all those tonight. Wonderful. Your final exam is 2 weeks from tonight. I mean, 2 weeks from tomorrow night. Sorry, not tonight, tomorrow night. Today's Wednesday. I'm still mulling over how we're going to do asynchronous work that last week of class, because I can't end the class on Thursday and then have you do asynchronous work the following weekend. That doesn't make any sense. I'm thinking about it. All right, just a reminder, your test is Monday, which is the 19th. That's going to cover chapter 4, whatever we do from chapter 4, which is going to be 4.2, 4.3, 4.4, 4.6, 4.7. The last thing I wanted to do from 4.4 continued is just going to be the local extrema piece. We talked about concavity. We talked about using the first derivative test to find local extrema, but now I want to talk about using the second derivative test to find local extrema. Hold on, this is going to drive me crazy if I don't get it to move, and this mouse doesn't like me. There we go. Local extrema. So I'm going to give you a test to find local extrema. It's called the second derivative test. Now, if you're thinking like, oh, cool, this is awesome, I don't always have to use the first derivative test. Not necessarily. It's kind of like how when you're trying to solve a quadratic equation, sometimes you can factor it and solve it that way. And if you can, your life's a lot easier. And so you always try to factor it first. But sometimes a quadratic equation is not factorable, and then you have to use the quadratic formula, but the quadratic formula works every time. It's kind of like that situation here with the second derivative test. The second derivative test works sometimes, and if it does work, it's usually easier to use than the first derivative test. However, if you start out using it and then it fails, you're going to have to go back and use the first derivative test. But the first derivative test works all the time. Okay, this is actually just called the second derivative test. I always call it the second derivative test for local extrema because sometimes students think the second derivative test is a test for concavity. And I know that you use the second derivative to test for intervals where your function is concave up or concave down. However, the second derivative test is actually used to find local extrema. That is officially what it is. So I tend to add that to the definition so you don't get confused. Let f be a function for which f prime and f double prime exist on the open interval from a to b. Suppose C lies in the open interval from a to b. And is a critical number of f. Okay, so C is a critical number of your function. You have to take the first derivative to get to the second derivative. So you're going to find the first derivative and you're going to get the critical number from there. And then you're going to keep going and you're going to get the second derivative. And here's where the test comes in. If f double prime of c is less than 0, and this is going to be one of those opposite things. So if your second derivative evaluated at the critical number is less than 0, then f of c is a local maximum value. So remember, c is a critical number, but as long as we can take the second derivative, evaluate it at the critical number, and show that it's negative, then we can say that f of c is a local max. So when I'm saying it's an opposite thing, it's because normally when we see less than, we think minimum. But for this theorem, less than is going to give you a local max. If f double prime of c is greater than 0, then f of c is a local minimum value. So that covers two scenarios. One scenario is where your second derivative evaluated at the critical number is negative, and for the other one, it's positive. If the second derivative, however, evaluated at your critical number is not negative or positive, it's 0, then you cannot use the second derivative test, and you have to go back and use the first derivative test. So that is an unfortunate situation, but it can happen. Go ahead, Renee. What's your question?
What's the point of using the second derivative test if the first one works all the time?
So assuming the second derivative test works, a lot of times it's just faster. I mean, honestly, I find that students don't use it a lot because it won't always work. I'm going to be using it actually quite a bit when we go through optimization problems in 4.7, because it's going to work for all those problems and it's just faster. And like I said, your Calc 2 teacher is probably going to use it from time to time, or at least reference it, and it's important for you to know what it is. So it's really, if you're asking what is the point of it, it's just, I mean, it's another way of doing the same thing. And like I said, you'll find that sometimes it is easier. So I'm going to show you an example, and you're going to be like, oh, wow, that was a lot easier than using the first derivative test. But then depending on the function, that might not always be the case. So it really just kind of depends on the function that you're working with, to answer your question.
Okay, thank you.
You're welcome. Yeah, it's kind of like, even though you know the quadratic formula always works, you still try to factor it first, because factoring gets easier. So if it's something where you can easily do it, you just do it. And then you might find out like, it's not factorable. Got to use the quadratic formula. But you still try anyway. Guess that's what I'm thinking. Okay, so I'm going to give you an example. I don't know what this is. Example 2. Use the second derivative test to find local extrema if possible. So A, I'm going to give you a polynomial function. X to the 4th minus 8x cubed plus 18x squared. So first I need to obtain critical numbers, and I'm going to do that using the first derivative. So f prime of x is 4x cubed minus 24x squared plus 36x. And from here, I'm going to get some critical numbers. I'm going to go ahead and factor out a 4x. That leaves me with x squared minus 6x plus 9. I'm going to set that equal to 0. And when I factor this, I'll get x minus 3 and x minus 3. It's a perfect square trinomial. And I'll get x equals 0 and x equals 3 as critical numbers. Now, even if you were using the first derivative test, you were going to have to do this anyway. So that's not a departure from what you did before. You still needed critical numbers. But if you were using the first derivative test, here is where you would set up intervals and use test points and look at the sign of f prime. With the second derivative test, we're going to take the second derivative, and I'm going to do that from this line where I still have my trinomial here. So I have 12x squared minus 48x plus 36. Don't set it equal to 0, because remember that when we're using the test, what we're doing is we're taking f double prime, evaluating it at c, which is the critical number, and we're just looking at, is it positive, is it negative, or is it equal to 0? So don't set it equal to 0. I know sometimes we get into that habit of just automatically taking a derivative and setting it equal to 0. Okay, so I'm going to take first my critical number at x equals 0. Doesn't matter which one you do first. And I'll get 36, because 0, 0 plus 36. This is greater than 0. That means that I have a local minimum at x equals 0. And the point would be 0, f of 0. F of 0 is actually 0 in this case, because f of x only has variables in every term. Okay, so see how easy that was? I didn't even have to use the first derivative test. I didn't have to find a test point. This is why people like the second derivative test, because depending on your function, it can be a little faster. However, we're not done with it yet. Now you have to take f double prime of 3. And f double prime of 3, you will find actually equals 0. So you were able to get some information from this, but not all of the information you needed. The nice thing, though, is if you do have to go back and use the first derivative test, which we will in this case, we don't have to look at every single interval, because we already know that at our first critical number, we have a local minimum. So let's say you did set up a chart and you included the first interval. Well, you don't need to even say anything about it, because you know that you have a local minimum at 0. If you have a local minimum at 0, that means that you had a situation where your function was decreasing and then increasing. It must be the case. So you already know most of what you would need to know for your first derivative test. What you need to know at this point is what happens here on this interval. So in this interval, I'm going to get a test point. I'm going to test for, and I'm going to take f prime of our test point, because I'm using the first derivative test. And I'm going to go back to f prime, which is up here. Actually, I'm going to use this variation of it because it'll be a lot easier to evaluate. 4 times 4 is positive. 4 minus 3 is positive. 4 minus 3 is positive. A positive times a positive times a positive is still a positive. Most of the time, you'll find that when your second derivative test fails, it's because you didn't actually have any extrema at that value, especially for polynomials. So in this case, you had a local min at 0, but we don't have any sort of extrema occurring on the interval from 3 to 0. Go ahead, Morgan.
I know you got 0 for like the local min, but how did you get the 0.00?
Oh, I just looked at the original function f and just knew that, okay, if x is 0, I'm taking 0 minus 0 plus 0. I just kind of quickly scanned it over. Because it's really just 0f of 0.
Okay. Okay, thank you.
You're welcome. Okay, other questions? Victoria, go ahead.
I just noticed that you put 3 to like 0. Did you mean to put 3 to positive infinity?
Yes, I did. I was probably
Yeah.
saying 0, and then I wrote it because I was saying it. Thank you for telling
No,
me.
you're good.
I should have thought that that looked weird, but I don't know. Didn't catch it. Thank you. Yes, that is the interval from 3 to infinity. Okay, so the conclusion here is that we don't actually have any extrema at x equals 3. So we have a local min at 0, 0. And then x equals 3 is neither a local max nor a local min. Use every square inch of this paper. Now, if you want to graph your original function, I'm going to plot f of x. It's x to the 4th minus 8x cubed plus 18x squared. And you can look at the graph. I don't know what kind of zoom we need here, but I'm in Zoom standard, so let's see what's happening. What we should find, yeah, that's because f of 3 is, I think f of 3 is probably a pretty large value. Let's see, f of 3 is 27. Okay, so when you're looking at the graph, at 327, you're expecting that something occurred here because that was a critical number of the function. So like, let's say I go back to the window and I set my x min to be, it doesn't even matter. Let's just go from 0 to 5 for x. And then for y, and we just need to go up to 27. So maybe I'll go like from 20 to 35. Oh, I did that backwards. And we'll see kind of what's happening there. We should be able to see this blip in the graph though, because we know there's a horizontal tangent line at x equals 3. Our question is just like, what's actually happening at that horizontal tangent line? So x equals 3 is right here. So there it is. You can see that at this point 327, your graph starts to level out, and it levels out to the point where you do get this horizontal tangent line occurring when x equals 3. However, you don't end up seeing that the graph heads back downward. The graph will then continue to go upward. And this is why x equals 3 is a critical number. However, it's not representing any local extrema because you don't actually see that you have a minimum or maximum value at that point. So this is a situation you'll sometimes encounter. So I don't want you to always think that every time you have a critical number, it will yield any sort of local extrema. It's not always the case. But you did see, going back to the standard zoom, that at x equals 0, we can verify that we have a local minimum at 0, 0, which is exactly what we came up with in our data. I'm going to do one more example of this. Does anyone have a question on A? Because then we're going to get into curve sketching, which I automatically get excited about. Oh, love it. Let's do B. Life would not be complete without a natural log function. F of x equals the natural log of x minus x. Remember that anytime, especially anytime you see a function that has a restricted domain, it's very helpful to write out the domain so that you have a good idea where your intervals should lie should you need them. Just wanting to make sure. All right, so x, of course, I mean, our domain there would be all real numbers, but we're restricted by the natural log of x. I'll try to focus this. For whatever reason, it always looks fine on my screen, but then when I look at it on the Meet screen, it looks blurrier. It's a little better. You'd think it would look the same. If my internet is choppy, let me know, because for some reason I thought something weird was happening when I logged on here. And my Peloton has been acting real crazy, which is very upsetting. I was having a milestone ride last night and it kept like flickering and I was on a PR. Luckily I finished it, but man, I was really, really concerned. And then my cool down ride, my internet somehow, like, it wasn't even the internet. I don't know what happened. It just froze and weird things have been happening. I think our puppy might be chewing on some of our wires out there, but my husband insists it's not happening. Don't know, but it's upsetting. All right, so here's your function. I need the critical numbers first. In order to get the critical numbers, I'm going to take the first derivative. I'm going to set it equal to 0. So for my first derivative, I have this situation. I want to be consistent here about what I've been doing all along. So I'm going to write this as one fraction, and then we're going to look at the numerator and denominator separately. So I'm going to rewrite f prime so that I have 1 over x minus x over x. That's a minus, so 1 minus x over x. So we're going to take f prime of x and set it equal to 0. When we do that, we have 1 minus x equals 0. And then we have x equals 1. Double check that 1 is in your domain. 1 is between 0 and infinity, so we're good there. There's a critical number. The other situation would be that f prime does not exist. And this happens when the denominator is equal to 0. But remember that 0 is not in the domain. We cannot take the natural log of any number that isn't strictly positive. So this is not a critical number. So we only have one critical number to worry about, and we're going to hope that we're going to take the second derivative and everything's going to work out beautifully. If you want to rewrite your first derivative using a negative exponent, that'll probably make your life easier. Go ahead, Renee. What's your question?
Can you explain why? Can you explain again why x equals 0 is not in the domain when it's in the coordinate?
Oh, so it's not. If it was a bracket, that would indicate that the smallest value we could use would be 0. But since it's a parenthesis, that means that any value that's greater than 0, so even like 0.0000001 is okay. Remember that your natural log function is only defined for values of x that are positive. That's a college algebra thing. But if you don't remember, you can always graph it and get a kind of an idea of what's happening. It actually has a vertical asymptote at 0. So the graph can never actually attain the value of x equals 0.
Okay, thank you.
So your natural log function, it's just a definition for the natural log function that you learned but maybe forgot. Its domain is just strictly positive numbers. I'm glad you asked because someone else was probably wondering that. Okay, so we have f prime right here. I'm going to rewrite this as x to the negative first minus 1, just because it's going to be easier to take the second derivative if we rewrite it that way. Notice that we can just kind of keep rewriting things to serve our needs at the moment. So now when I take the second derivative, I'm getting negative x to the negative second, and then the derivative of 1 is 0. So I can rewrite this as negative 1 over x squared. That'll make it easier to evaluate. And what I'm looking for here is I'm going to take the second derivative and I'm going to evaluate it at the critical number, which is 1. And then we'll see here if we have a negative or a positive value here for the second derivative. So I'm going to take -1 divided by 1 squared, and we will get -1, which is less than 0. If the quantity is less than 0, then our critical number will give us a local max. And that's happening at the critical number x equals 1. The point would be 1 f of 1. And f of 1 is ln1 minus 1. ln1 is 0. So your point would be 1, -1. And that's that. Geez, I put a sweater on because I was freezing, and now I'm just like burning up over here. It's terrible. Okay. That was the second derivative test for local extrema. Any questions on that? Excellent. All right. So I had mentioned that section 4.5 is a Calc 2 section at ECC. I don't know why. Students who take AP Calc in high school, even if it's just AB, usually learn L'Hopital's rule. If you took honors Calc in high school, you probably learned L'Hopital's rule. We don't cover it here in Calc 1. I don't know why. I guess because technically it's mostly just used in Calc 2 for the applications that are there. So maybe they just wanted to wait until you were about to extensively use it rather than having to review it. That's possible. And I guess it's really only included in chapter 4 just because it is technically an application of the derivative. And that's just kind of the way it worked out. Some books don't put it there, some do. Either way, we're not covering 4.5. So if you take Calc 2 at ECC, you will see 4.5 there. If you took it in high school and you've already seen it, sorry, but you can't use L'Hopital's rule here. But you would have used it back in like chapter 1 anyway. You won't really need it here in chapter 4. So we're going to move into 4.6 using calculus to graph functions. Which is my favorite of all the sections. It's hard to choose a favorite. I'm gonna go point this fan at me. Hold on. Maybe. Whatever. So what we're going to do here is we're going to combine all of the information that we have learned so far in chapter 4 to graph functions by hand. Now, technically, there's nothing to stop you from graphing them in your calculator, but I'm going to ask you to show all of your work on your exam, and you're going to have to actually show me each piece. So if you just graph something that was clearly just copied from your calculator, that's not going to fly because the work needs to be supported. I mean, it should go without saying. I think sometimes students are like, well, I don't know, so I'll put down something, and then they just copy the graph from their calculator. I mean, I understand you don't want to leave it blank, but at the same time, I already know that you know how to use your calculator to graph functions. The point here is that you need to be able to do it by hand. So that's what we're going to do now. Now, all right, I try to be very, very, very particular about the steps in which I do these problems. because there are a lot of steps that are involved. And if we just kind of go about this willy-nilly, some things are going to get forgotten about. So I'm going to give you a list of things that we need to look for, and then I'm going to try to follow these steps with each one of the functions that we graph, so you get very used to kind of following this procedure. Now, some of you will love that because you're very procedure oriented and you like to do things just right. And for others, this will drive you crazy because you just have work all over the place and you eventually figure it out, but you know what you mean, and it's hard for me to know what you mean. If you label your work, it's going to be easy for me to see what's going on. But these problems are going to take some time to get through, especially the first couple examples that I show you. It's going to take me maybe 20 minutes to get through the first one because there's a lot that we need to go through. So just keep that in mind. There's going to be a lot of information. The better you label it, the easier it's going to be for me to find on your exam. The faster you'll get your tests back. And then the less likely I am to miss something that maybe you thought was obvious, but I didn't see. Okay, if you have a graph paper, you're probably going to find that helpful. You don't have to use it. I find that most students don't use it. I will not be using it as I go through this on my blank paper. So it's kind of up to you. I also wanted to mention that this is probably the only section in your book for which I'm going to request that you do homework by hand, and you're going to have to submit it to D2L. So I'm going to give you some exercises that I want you to start on at the end of today's class, just to sort of get your feet wet, and then you'll be submitting those to me through D2L. Yeah, so that's kind of the way that's going to work. If you don't have access to the book, you can let me know. I'll probably just send it in an email attachment, just the list of exercises that I want you to do, just because I don't want you to think like, well, I can't do them because I don't have the book. Don't do that. Just ask me to send them to you. It's not a big deal. Okay. If you have an old edition of the book, your exercise numbers might be different. Keep that in mind. You might want to double check that with me. Okay. So we're going to look for a series of pieces of information here. The first one is going to be the domain. So first, we're going to find the domain and any intercepts. If you, when I'm done with these 7 steps, want to put a giant box around this or highlight it, as long as it's easy for you to find, I just want to make sure that you understand everything you're supposed to find and you don't miss any of it. The second thing you're going to do is identify any asymptotes and examine the end behavior. So today I'm mostly going to be focusing on rational functions. When we're talking about rational functions, asymptotes are going to be a huge part of your graph. We're going to talk about horizontal asymptotes and vertical asymptotes. End behavior is more for when you're working with polynomials. We did discuss end behavior in this class when we were talking about limits and infinity. So kind of depending on the degree of your polynomial, as x went to positive or negative infinity, what happened to the y value? Did they both go up? Did one go up and the other went down? So on and so forth. We did that when we were talking about limits and infinity back in 2.7, I want to say. But I'll remind you of that when we actually get to the polynomial functions, which I'm going to put in your asynchronous work. So if you remember, I'm kind of splitting this up. I'm going over curve sketching with you in person here. It's synchronous. Tomorrow we're going to talk about optimization in 4.7, and then the rest of the curve sketching will just be more examples, different types of functions. I'm going to just include in your asynchronous work because I don't want your asynchronous work to be totally brand new stuff when you have a test the following Monday. So it's going to be just more of the same. Step 3, find f prime of x to find critical numbers, then find f double prime of x. Okay, so you're going to go through this process here. You're going to find the derivative, find the second derivative. When you find the derivative, you're going to get your critical numbers. Then you're going to find intervals where f is increasing or decreasing. You are going to use the first or second derivative test to identify local extrema. You're going to find intervals where f is concave up or concave down. And then you're going to use the info to graph f of x. Plot additional points as needed. Now, the way I'm going to do this, and the way I suggest you do this, is that we're going to go through 1, 2, and 3, finding the domain, intercepts, asymptotes, end behavior, critical numbers, and the first and second derivatives. 4 through 6, we're going to pick out of a chart that we're going to create. I'm going to write here, chart. And on your test, I'm going to ask you to make me a chart that includes all of this information. And I'm going to do this for every single one of these problems. If you make yourself a chart, all of the information is just going to pop right out of your chart, and you're not going to have to sit here and do a whole bunch of different processes. But it's very important that we have the skeletal structure of the chart ready so that we can start to just plug in a bunch of numbers and pull out the pieces. And you will see how that works when we get there. Let's see. Yeah, that's good. These are the steps that you're going to need. So example 1, like I said today, I really want to focus on rational functions. F of x is negative x plus 4 divided by x plus 2. The negative is on the x in the numerator. It's not in front of the fraction. So the first thing we're going to do is find the domain and any intercepts. Now, I want you to consider here what we talked about as far as finding vertical asymptotes. Any value that's going to make your denominator 0 is going to be excluded from the domain. And it doesn't matter whether it's a removable discontinuity that you can factor and cancel. Any type of discontinuity in the graph is going to represent a vertical asymptote, or I'm sorry, I said that backwards. Any type of discontinuity in your graph is going to be excluded from your domain, I should say. But right now, we're looking at the denominator, and we're noticing that the situation here is that if x equals -2, the function's not defined. So if you want to label this as like, I'm just going to label it as like domain, I guess. And instead of labeling it as 1, 2, 3, 4, 5, 6, 7. X plus 2, we'll set it equal to 0 to find the values to exclude from the domain. And then you'll get that that value has to be x equals -2. If you want to set it not equal, maybe that makes more sense. You can write it like that. List your domain in interval notation. Any value from -infinity all the way up to -2 is fair game. And then any value from -2 to +infinity, also awesome. It's just that we can't let x be equal to -2. All right, so that's the domain of your function. Very important. Any pieces of information that I find really important, I'm just going to put a box around. I also need to find any intercepts. Now, for some of you, it's been a while since you've actually talked about finding x and y intercepts. So I'm going to remind you of that now. And the intercepts, a lot of times you'll find are very helpful to you. Sometimes it's just like 0, 0, and that point would have come out of somewhere else, and it's not that exciting. But sometimes the intercepts are really helpful. To find the x-intercepts, let y equals 0, which means we're taking f of x and setting it equal to 0. Remember, your x-intercept occurs when you're sitting on the x-axis. That happens when y equals 0. So you're going to take your function and set it equal to 0. To find the y-intercept, there will only be one because it's a function. You can't have more than one. We're going to let x be 0, and that means we're finding f of 0. So we have that. Let's go ahead and find the x-intercept. We're going to do this by taking our function and setting it equal to 0. Now, remember that we kind of talked about this in the last 2 sections. In order for your fraction to be equal to 0, you need the numerator to be equal to 0. So you're just going to take this and just pull out the numerator and set that equal to 0. Because if the denominator is 0, your rational expression will not be 0. It'll be undefined. And when you solve this equation for x, you'll get x equals 4. And then you should be really, really excited because it's not 0. It's an actual result that's going to lie somewhere other than at the origin. And this is actually going to be some useful information for your graph. You found x equals 4 by letting f of x equals 0. This gives you the point 4, 0 on your graph. An x-intercept always occurs on the x-axis. When you are on the x-axis, y equals 0. So f of 4 is 0. So that's your x-intercept. Now you're going to find your y-intercept. To find your y-intercept, you are finding f of 0. Back to my function here. F of 0 is negative 0 plus 4 divided by 0 plus 2. F of 0 is 2. 4 divided by 2 is 2. So what you just found was that when x equals 0, f of x equals 2. When you are a y-intercept, you're sitting on the y-axis. The only way for you to sit on the axis is for x to be equal to 0. So make sure that you don't flip those coordinates. All right, so we found the domain, we found the intercepts. Any questions so far? Wonderful. The next thing we're going to do is identify any asymptotes. Now, the vertical asymptote, we shouldn't have a hard time finding at all. The vertical asymptote occurs at any value where you have a non-removable discontinuity. So in this case, you're looking at your function and you're noticing that we already said that -2 is excluded from the domain. Well, there's no way that you can factor something out here and cancel that discontinuity. There's no way to get rid of it. It's definitely representing a vertical asymptote on your graph. Remember that if we could factor and cancel the x plus 2, then you would just have a hole at -2. However, there's nothing you can factor and cancel, so you would say that you have a vertical asymptote at x equals -2. That's going to be very important to us. We already excluded it from the domain, but now we're just formally stating that it's a vertical asymptote. I'm going to remind you now of our rules for horizontal asymptotes. Remember, I gave you 3 different cases, and I know it seems like so long ago, but it really wasn't. We talked about horizontal asymptotes, and I believe it was it 2.7 in this book? We change books all the time now. I used to know every section so well. It's either 2.5 or 2.7. When we talk about limits and infinity. Maybe it's not even chapter 2. Maybe it's I think it's 1.5 in this book. Either way, we said that if the degree of the numerator and denominator is the same, then your horizontal asymptote is y equals the ratio of the lead coefficients. We remember that? Seems like forever ago. I think it was section 1.5. So your horizontal asymptote is y equals the ratio of the lead coefficients, which in this case is y equals -1. So here's your function. Your lead coefficients are -1 and 1. The ratio of those lead coefficients is -1. Yeah, I had given you, so the other 2 cases were if the degree of the numerator was greater than the degree of the denominator, or if the degree of the numerator was less than the degree of the denominator. And I think I showed you guys a trick for always just making the degrees the same. So when we come up with that, I'll remind you of what that trick is. But for now, for this function, are there any questions about the asymptotes? So notice that really we haven't even done any calculus at this point, and we know a lot about this function. We know 2 points that lie on the graph, and we have 2 asymptotes, one vertical and one horizontal. This is actually a lot of information so far. All right, so that was number 2, which was asymptotes and end behavior. The end behavior is not going to apply to rational functions because we have the horizontal asymptotes. Find f prime to get the critical numbers, then find f double prime. And then once we find those things, we're going to go ahead and make ourselves a nice chart. Hold on to that because I know I'm going to need to reference it. Okay, so I'm going to rewrite my f of x here. F of x is negative x plus 4 divided by the quantity x plus 2. We're going to use the quotient rule here to find f prime and then f double prime. So f prime g minus f g prime. Don't forget to divide by g squared. Now remember, we're looking for critical numbers here once we simplify our derivative. We have negative x minus 2 plus x minus 4. Negative x plus x gives you no x's. And then in your numerator, you can simplify that to negative 6. And if I were you, I would put a big box around this so that you can find it easily. Okay, now it's kind of up to you. Sometimes in situations like this, I would rewrite this with a negative exponent and use the chain rule, but you might find that it might be easier to simplify this one if you just use the quotient rule. I'm just going to go quotient rule in this case, just so not make any waves. So f prime is 0, g minus f, and then g prime needs the quotient rule. But when you multiply by the derivative of the inside function, you're really just multiplying by 1. The exponent went down to 1. G squared is going to be x plus 2 quantity squared squared. Prime g minus f g prime. And then we'll simplify. So a negative times a negative here in your second term gives you positive, and then 6 times 2 gives you 12. The x plus 2's, well, this whole term goes to 0, so you don't need to worry about this term. You can cancel out one factor of x plus 2 in the numerator and denominator and just write this as 12 divided by x plus 2 quantity cubed. And this is, again, f double prime of x. Make sure it's labeled, put a box around it. You'll be looking for it in a few minutes. We do need to find the critical numbers. We'll do that real quick. But does anybody have a question so far on f or f double prime? All right, so to find the critical numbers, we're going to take our derivative and we're going to do two things. One of those things is set it equal to 0. Well, you can see that this is a waste of time because negative 6 cannot equal 0. So you're not going to get any critical numbers to pop out of the numerator. And as far as the denominator is concerned, we're looking for f prime of x does not exist. And that's going to happen when your denominator equals 0. However, this happens at x equals negative 2. X equals negative 2 is not in the domain of f. We found the domain at the beginning of the problem, and we excluded negative 2 from it. So this can't be a critical number. Now, this means we have no critical numbers, which means we don't actually have any relative extrema. So you're not going to have any local mins or maxes. That's an interesting thing to have happen. So we would say we have no critical numbers. And this means no local extrema. But you know what we should do here? Before we make our chart, is look for any possible points of inflection. I should update number 3 to say, then find f double prime of x and possible points of inflection. Because we really should list those out before we make our chart. It's going to be important to us. Okay, so let's do something similar with the second derivative and look for possible points of inflection. And these will occur when f double prime of x equals 0. Well, guess what? F double prime of x can't be equal to 0 because 12 cannot be equal to 0. And notice again that when f double prime of x does not exist, you're dealing with another situation where if you set the denominator equal to 0, you get x equals -2, which is not in the domain of the original function. What that means is that you have no possible points of inflection. And this means no changes in concavity. Okay, now, with that being said, I'll give you a second to write that down here before I give a very important caveat to that statement. Okay, now, when I say that the concavity can't change, we're talking about what's happening actually on the domain of the function. Now, remember that you have a vertical asymptote at x equals -2. It's possible that on each side of the vertical asymptote, your concavity could be different. However, we can't actually say that we have a point of inflection on a vertical asymptote. The concavity might be different on each side, but that's a major discontinuity. It can't possibly be a point of inflection. I want to make sure that's clear. And I think that you might see, yes, you will see that situation appear with the graph. So I'm going to make sure that I reiterate this when we graph this function, that even though your concavity is going to be different on each side of the asymptote, that does not mean you have a point of inflection because you're not actually looking at a smooth continuous curve where all of a sudden your concavity changes from up to down or vice versa. Next, we're going to make our chart. Before I do that, does anyone have a question on the information that we have acquired thus far? You're going to find that some of these are more straightforward than others. This one is definitely more basic, which is why it's the first one that I'm showing you. Give yourself some space for your chart. We're going to do all of these the same way. Okay, what we're looking for when we make our chart is I need to take all the important information and put it into the chart. So that means that if I have critical numbers or if I have possible points of inflection, those need to go in the chart. And I'm going to set up intervals the way that I would set up intervals back in section 4.3 and in section 4.4. when I was doing the increasing, decreasing tests and the concavity test. The difference with this chart is that everything is getting combined into one. So you need to think ahead about all of the important pieces of information. We did not actually have any critical numbers. We did not actually have any points of inflection. That doesn't mean that you just have a chart that goes from negative to positive infinity, because you do have a very key piece of information about this graph. And that is the fact that you have a vertical asymptote at -2. You could have, like I said, different things occurring on each side of that asymptote. So it's really important that we split up our intervals at the asymptote, because it's almost like two different ball games on each side of your asymptote. So I'm going to go ahead and set up my chart. Let me keep this over here in case I need to reference it. And I'm going to do this a little bit more. I don't mean to say neatly, but I'm going to be a little bit more formal about the way that I make this chart. First of all, we are definitely going to need test values. So we're going to need that. And you're going to start the way that we always would start any chart, at the lowest value in your domain. And then you're going to work up to either the first point of inflection that you have, the first critical number that you have, or the first vertical asymptote that you have. Vertical asymptotes have to go in the chart. They must. And in our case, we have a vertical asymptote at -2. And then we're going to actually include here a column for -2. You're going to find it's not going to necessarily be that helpful in this particular example, but in future examples, it's going to make a huge difference to us that we're actually including that key X value in the chart, so that we can make some conclusions about what's actually happening to the graph there. Now you're going to get some test values. You're going to also evaluate the function at your test values. Normally, we only talk about looking at the first and second derivatives at your test value, but we're going to look at all the values in this case. So we're going to look at f of x, and even if x is your test value, we're going to do that too. Just because it's going to actually give us more points to graph. You'll find that that is the case. And then you're going to make conclusions. And I'm even going to make some nice lines for my chart. Remember, on your test, I am going to ask you to make a chart so that I can easily see all of the information that you've obtained. Okay, we have no critical numbers, no points of inflection, so the only thing going in your chart is your vertical asymptote. Now, we already know our conclusion for x equals -2 is that we have a vertical asymptote there. So if you want to just note that so you don't have to worry about it any longer, that's fine. Now you're going to come up with some test values. Pick whatever you want. If I were you, I'd pick something that you can actually graph. The nice thing is we're actually going to find the function value here so that we can pop these points onto the graph. So don't pick something like -100, because that's not going to help you when you go to graph it. So maybe -3, probably 0. You guys know I like 0, just easy to work with. And of course, we don't need a test value in here because we're looking at the actual value, x equals -2. Okay, now we're going to put this into our graphing calculator. And I would like for you to do the same thing every time. So we're going to plot the original function, its derivative, and its second derivative. Now, I would hate for you to do all this work and then enter it into your calculator the wrong way. So please make sure you're being very careful of how you enter this. The original function is parentheses, -x plus 4, parenthesis, divided by, open up parenthesis, x plus 2. That's the original. Your first derivative is -6 divided by the quantity x plus 2 squared. And your second derivative is positive 12 divided by the quantity x plus 2 cubed. And note that each time you took this derivative, you ended up getting another power in the denominator. That's what you expect. You should be able to see that pattern as you work your way through here. If you don't, double check and wonder, did I miss something? Okay, now what we're going to do, and it's going to be transposed here. We're going to go to our table. Now, in y sub 1, these are going to be all the function values. In y sub 2, these are going to be all the first derivative values. And the column for y sub 3, you're going to have all the second derivative values. Now, we only care about what's happening at our test points, -3 and 0. So like I said, this is kind of confusing because it's going to be transposed. What I mean by that is your f of x row goes horizontally, whereas in your calculator, it's vertical. So if you want, just fill out one row at a time. That's what I'm going to do. So for f of x, at f of -3, the function value is -7. And at 0, the function value is 2. And now I'm going to work on my derivative, and then I'm going to work my way left to right, top to bottom. So at -3, y prime is -6. And at 0, y prime is -1.5. And then for f double prime, I'm looking at y sub 3. At -3, it's -12. And at 0, it's positive 1.5. Okay, I'm done with my calculator at this point. Does anybody have a question about how I use the calculator to fill out the table? Excellent. All right, remember the derivative is representing whether your function's increasing or decreasing. The derivative in this case was negative at our test point -3. So I know the function's decreasing. It's also negative at 0. So I know the function's decreasing there also. Remember that f double prime represents your concavity. It's negative at -3. So we know the function's going to be concave down, frown. At 0, we know the function's going to be, if the second derivative was positive, concave up, cut. You don't have to make these conclusions in your chart. As long as they're on the bottom row, that's all I care about. I kind of just like to combine everything all over the place so you can see it in multiple places. Okay, so our conclusion is that on the interval from -infinity to -2, our function is decreasing, concave down. And then on the interval from -2 to infinity, our function is decreasing, concave up. So when we graph this, we need to match that behavior. Now, of course, I didn't actually look at the function value at -2 because I know it would be undefined, and it would actually be undefined for all of these. So we don't worry about those. Mostly we'll use it in future problems. I wanted to include it so you got used to the format here, but when it's a vertical asymptote, it's not going to make a difference to you. Victoria, what's your question?
My question is, when putting in the x values, so putting in -3 and then 0, my third one, I think, is, how did you get -12? Could you go back to the y values when you input? Oh, I see. Okay. I see what I did. Okay, thank you.
You're welcome. no problem. Yeah, I know it's very frustrating when I see that students have like the right first derivative and the right second derivative, but then the values in their table are wrong. And I'm like, it's just that they couldn't get the signs right. It happens. Okay. Other questions before we graph this? Because we're ready to graph at this point. Okay, now, just a reminder, remember that f prime, f double prime, these test values were very important to us to determine what was happening with our graph behavior-wise. I never used to actually have students evaluate the function at the test value because it doesn't really tell you anything about the graph, but I started doing it because it gives you additional points on the graph. So if you know that f of -3 is -7, well, that's just one more point that you can plot. And if you know that f of 0 is 2, that's just, well, that's actually going to be your y-intercept in this case. But it's one more point that you can plot. That's the only reason I have students fill that out now, just because I feel like it makes the graph more complete. Okay, so let's go ahead. I'm going to make mine large so everyone can see what's going on here. Now, before you make your graph, it's going to be helpful to you if you kind of decide right away what kind of scale you need to use. And you're going to do that by determining the values that you're going to be plotting on your graph. Like, for instance, I know I have a vertical asymptote at -2. I have an x-intercept at 4. I have a y-intercept at 2. And my asymptotes are still under 5, or between -5 and +5. Really, the only value I have that's larger than the absolute value, or the absolute value is larger than 5, is this one, which is -7. Anything else that I'm going to plot point-wise is not going to be any less than -7 or greater than like 4. So you don't have to get too crazy here about labeling this from like 20 to 20 or something. I would maybe just go to 7 in every direction if you know that's the largest value you have. So kind of look at what you need first before you set up your scale. And, you know, do the best job you can squaring this out. There will be instances where maybe you need to change the scale so that it's different on the y-axis than the x-axis. Maybe your graph is like really narrow and you need to, you know, go up to like, you know, 50 or something, but your x values only need to go up to 5. And that's something that you're going to have to gauge. It's part of what you need to learn here. But do the best you can. Trying to make these equidistant. So something like that. Now, my recommendation to you is to always start out plotting the asymptotes. Those are going to be the easiest thing for you to graph that will make the hugest impact on the actual picture of the function. So you have a vertical asymptote at -2. We've been talking and talking and talking about it. It gets graphed with a dashed line. Please don't make it solid. I will take off points. This is your vertical asymptote at x equals -2. We have a horizontal asymptote at y equals -1. If you'll remember, we found that early on when we were talking about finding horizontal asymptotes. Plot that. Just, again, do the best you can. It doesn't have to be perfect, although this is going to drive me crazy. It looks like it's descending to the side here. That's no better. Oh well, such is life. Okay, what I would do after asymptotes is plot the x and y intercepts. So you have an x-intercept that we found at the beginning of the problem at 4, 0, and you have a y-intercept at 0, 2. So I'm going to plot those next. So 1, 2, 3, 4. and 0, 2 is right here. So your x-intercept and your y-intercept. Obviously, but I'll label them anyway, just so you can see that we use them. Okay, now, once you've plotted any asymptotes that you have, and once you've plotted any possible points, oh, don't forget, actually, we have more points in our table. We tested f at -3 and found that the function value is -7. So it'd probably be a good idea to plot that. So at -3, 1, 2, 3, -7, we're about right here. This is going to be helpful to you to see this point. So this is -3, -7. It was obtained from the test value, so that you kind of know where everything came from. You don't have to label it like that. I just want to make sure everyone understands where everything's coming from. Never hurts to include more information. I know that's going to be an asymptote, so I'm going to need to run into that. So I'm just kind of moving my label. Okay. I also had a point at 0, 2 that came out of the test values. However, that is this point, which was my y-intercept. So unfortunately, that was a time when selecting 0 didn't really do that much for me. One of the few times. All right, so we have a whole lot of information. Let's go ahead and use now the conclusions from the table to graph this function, to actually put these curves together. We know that on the interval from -infinity to -2, so that's to the left of the vertical asymptote, our function is decreasing and it's concave down. So here's the part where you need to actually think about what your graph must possibly be doing in order for you to be decreasing concave down. If your function's decreasing, and we're talking about this interval from -infinity all the way up to -2, so we're just looking at this piece to the left of your vertical asymptote, the only way it can be decreasing concave down is for it to be in this little, if you want to consider it like a quadrant down here. To be decreasing, that means your function is going down from left to right. Remember that you can only cross your horizontal asymptote somewhere in the middle of the function. You can't cross it at the end. As x heads out towards -infinity, your function values have to be approaching this horizontal asymptote. You also have to be going through this point, which now you can see was very helpful to us. If you're going to be concave down, that means you've got a frown situation going on. And if you were to go through this point and go up to approach this asymptote, it must be the case that your graph has to be restricted to this lower quadrant of your graph, if you want to consider it like that. So you're going to approach the vertical asymptote, try to do a good job approaching it, not touching it. And then you're going to show that as this function is decreasing from left to right, its concavity is downward. So you don't have a cup situation. You have a frown situation. And you're going to approach the horizontal asymptote. I didn't do the best job approaching it, but I think at least you can get a good sense of what's happening here. So you can see now that your function is decreasing concave down from -infinity to -2. So decreasing is heading down from left to right. Concave down means if you tried to put anything in this cup, it would spill all over the floor. And it has to go through this point. You could always, if you needed to, plot additional points. Like for instance, if you wanted to know how close to get to the asymptote, you might want to say, well, let's let x equal -7 and see where the y value is. But I'm not super hung up on that. If I wanted you to just graph functions by plotting points, then we wouldn't be using calculus right now. I want a general gist of what's happening with this graph. I want all the important stuff labeled on here. And I want the important stuff to actually be on your graph. But as far as having each and every little point and getting the exact y value, it's not important. The important thing is that you understand the general behavior that's occurring in between these key pieces of information. We're going to work on the other side of the graph, but before I do that, are there any questions about this piece? So going back to our chart, we're going to look at this next leaf of the graph, which is on the right side of our vertical asymptote from -2 to infinity. And from there, we know that our graph is decreasing, concave up. And it has to go through these points. So in order for us to be inside these asymptotes, I can't cross them. I'm decreasing, I'm concave up. You kind of have an idea of what's happening. If you want to sketch something and just verify that it's doing what it's supposed to be doing, this function is decreasing and it is concave upward. All of its tangent lines lie below the graph. It goes through the necessary points. It's approaching the asymptotes but not touching them. Make sure that you include arrows to indicate that the direction of your graph continues on its journey. But this is what the graph looks like. You could double check it in your calculator, although that should just be a double check. You already have f of x as y sub 1. Graph it. There it is. Aw. I was going to say we did all of that without a calculator, but technically we used the table. But you could have done this with a scientific calculator. Just pointing that out. It's just easier to use the table in our graphing calculator. But, you know, evaluating a derivative at a test point, that's really just an arithmetic problem you could have done on any calculator. Okay, that was example 1. Berfin, what's your question?
So do we now use the points we got for like prime of f and like the second derivative and the first derivative, or no?
Oh, you mean these values?
Yeah.
Yeah, so remember, these aren't actually values on the function. The only values on the function correspond to f of x in your chart. These values are important because they tell us information about the behavior of the graph, but they don't actually lie on the graph.
Okay.
Yeah, I'm really glad you asked that, actually, because I didn't think to mention it, but I'm sure someone else was wondering. Yeah, the only ones that actually lie on your graph are these ones, because remember, this is the graph of f of x. The label for it. Sorry, can't see it anyway. This is the graph of f of x. If I was graphing f prime, then yeah, these points would be on it. If I was graphing f double prime, these points would be on it. But since I'm only graphing f, I'm only worried about plotting points that are in this row. These points are important just because they lead us to our conclusions.
Thank you.
Okay. Any other questions on example 1? I told you that would take some time. I will go a little faster through the next couple of examples just because I feel like when we do the first one, there's just a whole process and it's all very new, but you start to get the hang of it pretty quickly, and you've seen it now. But if you feel at any point that you have a question, please do let me know that you have a question. I don't think I'll be going too fast. I don't think I ever really go too fast, but I guess that all depends on who you are and who I ask. Some of you probably think I go too slow. Okay, so the thing about rational functions, and the reason I start with them, is because there are so many different things that could happen with rational functions. And even though some of the properties from one function to the next might be the same, you'll find that the behavior of the graph is very different depending on what all is occurring and what signs are in the graph. Like for instance, example 2, f of x is x squared divided by the quantity x squared plus 3. Now, notice that the first thing we're going to do here is talk about the domain. The domain of this rational function is going to be all real numbers because we don't have a minus sign here, we have a plus sign. So right off the bat, we're not going to have any vertical asymptotes in this particular rational function. But we're still going to deal with having a horizontal asymptote because the degrees of the numerator and denominator are the same. So there are going to be things that are similar in examples 1 and 2, and also things that are very different. So let's start with the first thing on our list, which was finding the domain of the function. I'm going to pull my list back out here so I don't forget the order in which I was going to do all of these things. Okay, so find the domain and any intercepts. The domain, put that wherever you want, is going to be all real numbers because I have this situation where x squared plus 3 cannot be equal to 0 and x squared cannot be equal to -3. Well, you don't need to worry about a value squared being equal to -3. So our domain's all real numbers. Then we'll look at finding the intercepts. To find the x-intercept, we're going to let y equal 0. That means we're letting f of x equal 0. And that's going to happen when the numerator equals 0. So to find the x-intercept, we'll set f of x equal to 0. And then we'll just take the numerator and set it equal to 0. And you'll get x equals 0. Now, unfortunately, this is kind of a boring result because it just gives you this point at the origin. Y was 0, x was 0. Fine. We'll still use it, but it's not going to give us a whole ton of useful information about our graph. To find the y-intercept, we'll let x be 0. So that means we're finding f of 0. And again, very boring. The y-intercept and the x-intercept are the same. They're both 0, 0. So again, like, okay, it's something, but nothing too crazy. Because remember, you want a lot of information out of here because these are points that you want to graph. I know sometimes we get 0, 0 and we think it's a good thing, but maybe not so much here. Next, we're going to find asymptotes. We do not have any vertical asymptotes because we cannot possibly have x squared equal to -3. So we can say vertical asymptotes, none. And that's because x squared cannot be equal to -3. Now, for your horizontal asymptote, we'll have some information out of this. It's going to be y equals the ratio of the lead coefficients because the degrees of the numerator and denominator are the same. So 1 divided by 1 is 1. Your horizontal asymptote is at y equals 1. This is because 1 over 1 is equal to 1. Okay. Questions so far? And I don't need to worry about end behavior in this case because I know that the graph is going to approach these horizontal asymptotes. That technically is the end behavior. The next thing we need to do is get f prime and f double prime and then look for critical numbers and possible points of inflection. And we'll use the quotient rule. Let's see. Well, you can hopefully see f of x on your sheet. Mine is kind of long gone. F prime g minus f g prime all divided by g squared So you will have 2x cubed plus 6x minus 2x cubed. Which is 6x divided by the quantity x squared plus 3 squared. And you're going to want that later when you put this into your calculator. So make sure it's labeled. Double prime. I was going to say, if you know, some of us are robots and we just want to go for the second derivative, like me. I guess you can find the critical numbers now and then find the second derivative, or you can just go for the second derivative. I'm in derivative mode, so I'm just going to find f double prime first, and then we'll focus on critical numbers and points of inflection. So f prime g minus f, and then g prime is going to need the chain rule. So I have twice x squared plus 3 to the first times the derivative of the inside function. Don't forget to square your denominator. And I always go through and double check. G minus g prime twice, x squared plus 3 to the first 2x. Okay. Now, the nice thing is that when you take your second derivative, you're going to get into this situation where each one of your terms has a common factor of x squared plus 3. You only have at most one of them that you can cancel out. So take out the x squared plus 3 here, take out one of them down there, and take out one of them there. And then simplify. So I have 6x squared plus 18 minus, and then be careful here, 6 times 2 times 2 is 12 times 2, which is 24. And then you have x squared. So many things can go wrong when you're working on these derivatives with your quotient rule. Look at the signs. Okay, you fix that. I need to put on my nighttime lighting in here because I cannot hardly see. Oh, okay. Then we'll have 18 minus 18x squared divided by x squared plus 3. Quantity cubed. And you can factor out an 18. Well, you don't really need to, but if you want to, you can. And we'll work more on that in a second when we look for possible points of inflection. And you know what? When you enter this in your calculator, you might even want the non-factored version. I don't know. You decide. Sometimes the fewer grouping symbols you have to worry about, the better. But this one I'm going to use when I look for possible points of inflection. Questions on the first or second derivative? So critical numbers are going to come from the first derivative. F prime of x equals 0 when I have the numerator equal to 0, which is 6x equals 0. And that happens when x equals 0. And again, double check that it's in your domain, but in this case, our domain's all real numbers, so we don't have to worry about it, but just make sure you're looking at that. We also need to worry about where we might possibly have a critical number where the denominator does not exist. And remember what that means is we have x squared plus 3 squared equals 0. Well, that is not going to happen. So we would say we have none there. So we have one critical number at x equals 0. And then we're going to look for possible points of inflection. And that is going to be where f double prime equals 0 or does not exist. And we already know it's not going to not exist. But this is kind of where you're going to use your squared version. If we take the numerator, I'm sorry, your factored version, not your squared version. Take your numerator and set it equal to 0. And then you can factor this using a difference of two squares. 1 plus x times 1 minus x. And then you're going to get x equals -1 and x equals +1. These are going to be values where you are possibly going to have points of inflection. I would bet they will be points of inflection. And then f double prime of x does not exist. Well, you're not going to have any of those for the same reason you didn't have any critical numbers where f prime did not exist. So in this case, we actually got some more information about critical numbers and points of inflection than we did in example 1. In example 1, we had more information that came from sort of algebraic things like intercepts and asymptotes. Whereas in this case, we didn't have as much of that, but we do have more information regarding the calculus portion. Next, we're going to make our chart. Before I do that, are there any questions about the information that we've obtained thus far? Okay. Terrific. Okay, so when I'm considering making my chart here, I need to include any values that are not in the domain. In this case, I don't have any. And then I need to include any critical numbers and points of inflection in my intervals. So in my chart, I'm going to need to cut off intervals at -1, 0, and +1. Put that right there in case we need it. So I'm going to have more intervals here because remember, I'm always going to have one more interval than I have pertinent pieces of information. And I have 3 pertinent pieces of information, so I'm going to have 4 intervals. I'm going to go from -infinity to -1, and then I'm going to look at what happens at -1. Because remember, if I end up having a point of inflection, sorry, I'm pointing at it and you can't see it. If I end up having a point of inflection here, I'm going to want to know what the corresponding value is for that. So I'm going to want to know, well, what is f of -1 so that I can actually give the point where the point of inflection occurs. Then we're going to go from -1 to 0. Then we'll go from 0 to 1. And then from 1 to infinity. We're going to get test values inside our intervals. We're going to look at f of x. We're going to look at f prime at the test values and f double prime at the test values. And then we're going to make conclusions. I'm trying to make my charts neat here so that I can keep all the information organized and I don't have a bunch of numbers running into each other. Oh, my night light means crazy lamp thing. Like I'm under some sort of interrogation. I'm going to enter my original function f, my derivative, and my second derivative. So the original function is x squared divided by x squared plus 3. Don't forget your parentheses. My derivative is 6x divided by x squared plus 3 quantity squared. Again, you should be seeing this denominator increase by another factor each time you enter it. For my second derivative, I'm going to enter this before I factored it as 18 minus 18x squared, parenthesis, divided by x squared plus 3 quantity cubed. Double check everything you entered. Make sure that it matches the data on your paper. Once you have entered all of your important information, you are going to go to your table. Oh, and we never even put down test values. Let's do that real quick. I don't know. -2, -0.5, +0.5, +2. That's easy enough. However, in the table, this time I don't have to worry about asymptotes where I don't have a defined value. So I am going to go ahead and enter in -1, 0, and 1, because remember, this value represents some sort of local extrema at 0, and then plus or minus 1 represent points of inflection. So I'm going to want to know x f of x, or c f of c, whatever we called them. So -2, -1, -0.5, 0, +0.5, 1, 2. 1, 2, 3, 4, 5, 6, 7 values. So I'm going to go through first looking at the f of x piece in my table, and you might do this slightly differently. Everyone's going to have a different way that they do this. Now, I'm going to eventually be plotting this on a graph, so it's not an exact value here at -2. It's 0.5714. Fine. It'll at least give us some sort of approximate value on the graph. At -1, f is 1/4, 0.25. At -0.5, we are at 0.0769. At 0, we have 0. At 1/2, we're at 0.0769. At 1, we are again at 1/4. And at 2, we're at 0.5714. And I'm just going to go through and I'm going to do the same thing for the second and third columns and the f prime and f double prime rows in my chart, respectively. So at -2, in my y-2 column, I'm at -0.245. Now remember, this is not something that I'm going to graph. The -0.245 is something that is dictating what's happening on my interval as far as whether my function's increasing or decreasing. However, oh, that got worse. I'm just going to leave it there. It's fine. At least you can see it at the bottom. This is terrible. There we go. -0.375. Oh, yes. Okay. That's fine. Honestly, though, do we really need f prime? No, we don't need those. You can list them if you want, but you're not going to be plotting these points, so it's not really going to matter to you. At -0.5, we have -0.284. At 0, we have 0. At +0.5, we have +0.284. And at 2, we have 0.2449. So if you want to go through and, you know, make your conclusions about increasing, decreasing now, that's fine. Don't have to. It's kind of up to you if you want to do that at the end or just kind of make some notes as you go along. So if the first derivative is negative, then your function's decreasing there. Kind of up to you how you decide to denote that. The reason I didn't bother including f prime at these values is because they're not going to go on the graph of f. They would go on the graph of f prime. And it doesn't matter to me what's happening here. And for instance, I know that f prime of 0 is 0 because that's how I obtained this value to begin with. It was the value at which the first derivative was 0. So, I mean, if you want to pop it in there, fine. You can see that it must be, in this case, a local minimum because this is where you had that horizontal tangent line. So kind of up to you about that. Mostly I just was trying to get function values everywhere and then f prime and f double prime at the test points. F double prime is in column 3, negative 0.157. And again, this is 0 because that's where you got your possible point of inflection from. It all depends on where I put my arm. 0.3933, 0.3933, and negative 0.157. And this is where you're getting your information about the concavity of your graph. So here we're looking at concave down, concave up because it's positive, concave up, cup, concave down, round. And there's a ton of information on all these random numbers. So we know that on the interval from negative infinity to negative 1, we have a function that is decreasing and concave down. Before I proceed with the table any further, are there any questions about how I obtained this information? I just want to make sure we're all on the same page. Wonderful. Decreasing concave up, increasing concave up, increasing concave down. Okay, now we have some new information this time that we did not have in example 1, and that information is occurring at x equals negative 1 and x equals positive 1 and 0. So remember, x equals negative 1 and positive 1 were considered possible points of inflection. That's where they came from. And x equals 0 was a critical number. Sometimes it helps to label that just so you remember what you were actually looking for. But the possible point of inflection at x equals negative 1, you can now verify it actually is a point of inflection because you're seeing the concavity change from down to up. So we can make a conclusion now regarding our point of inflection at negative 1, 1/4. So you're going to see that concavity change exactly at that point. Same idea with the point of inflection at 1. We said it's possible that the concavity is going to change there. Well, we just verified that it did. So we can now say that we have a point of inflection at 1, 1/4. Now, your critical number represents local extrema. So that's where we used our first derivative test to determine if our function was increasing or decreasing. Same idea here. We went from decreasing to increasing. So because we went from going down to going up, we would say that we have a local minimum at 0, 0. And again, it's nice that we have these function values because now we can just pull them right down. And instead of having to look at what the actual function value is there, we already obtained them from the table. That's our chart. We're going to use it now to graph the function. Before I do so, are there any questions on the chart? So it's very important mostly to understand what goes in the chart. It's possible points of inflection, critical numbers, and any vertical asymptotes that you have that represent discontinuities. Okay. Now, go ahead and look at the values that you're going to be graphing and dealing with. They're all very small. I mean, the only interesting stuff that happens on your graph happens between -1 and +1 inclusive. Now, that's where you're going to have these points. You've got another point at 0, 0. As far as our test values are concerned, they didn't even yield anything very large. I mean, you're just looking at these really small values. We had a horizontal asymptote at y equals 1, but again, that's a pretty small value that's not really going to be affecting much that's occurring in our graph. So in a case like this, it's actually going to be most helpful to us to make the scale very small. So because if we take this out too many units, everything's going to be smashed and we're not going to be able to see it. We want to really be able to enlarge this graph so that we can really see what's going on. I don't see any y values, for instance, that are greater than 2. We don't have any intercepts. Nothing is happening beyond that horizontal asymptote. If you want to take it up to 3, that's fine. Maybe just do that to be on the safe side if you're not sure. 2 would be enough in this instance. But I'm going to go 1, 2, 3. By the way, all this labeling that you're seeing me do, as long as you label the some tick marks, you don't have to label every single one, but I at least want to see you label the mins and maxes. You don't have to go through and label everything. And then, of course, label the x and the y-axis. My Calc 2 teacher actually took off points if we did not label the y-axis and the x-axis. And that's because he taught Calc 3 a lot. And in Calc 3, you're going to have 3 axes because you're going to include that z-axis. So it's going to make a big difference because you can orient your axes however you want there. Whereas here, it's pretty standard. In Calc 3, everything's just going to rotate. So it's a good habit to get into to always label your axes. Oh, I can already tell that that point is off, but whatever. Okay, so like I said, if you have asymptotes, I would graph those first. And we do have an asymptote, a horizontal one, which we're going to graph with a dashed or dotted line at y equals 1. Now remember that at the ends of our function, as x approaches plus or minus infinity, the graph is going to approach these this horizontal asymptote. We had an intercept, an x and a y intercept at 0, 0. Now notice, however, that this is also a local minimum for us according to our chart. So we know that this is going to be the smallest point at somewhere in here. You know it's going to do something like this. If you want to draw sort of like a skeletal variation of this graph and then sort of fill it in and adjust as you go through, that's fine. But because it's a local min, we know that it's going to bottom out there. So we found it first as x and y intercepts, but we also found it in our chart as a local minimum. You do, though, have points of inflection at plus or minus 1 and 1/4. So that's giving you some more information also. So if this is 1, here's a half. Well, a fourth is right there. So these are going to be your points of inflection, approximately. Do the best you can. And then you do have some additional points you can graph that came from your chart. Like, for instance, 2 and then 0.5714. So if you want to do that, that's fine. That's going to be just a little bit over a half. But I just pulled that from the chart. And then you can graph the other one over here also, which is going to be right about there. But now you can really see what this function is doing as it approaches the asymptotes. Now, I'm going to have this widen out a little bit. But we know we're approaching the asymptotes. The only way to do that is to come up from here. Your question is just, how do you approach the asymptote? And really, you can sort of gauge that the only way you can really do it is if you're concave downward. I mean, how could you be concave up and approach the asymptote? But I mean, note that you have to be concave down on this interval. So you're concave up from 0 to 1, concave down from 1 to infinity. So to be concave down from 1 to infinity, your graph is going to sort of, it's going to be hard to graph. It almost looks like it's diagonal in this case, but really it should be sort of displaying some concave down behavior. I'm going to see if I can make it look a little more concave down, but it's kind of hard to see. Do I have anything in between? No, I have points at 0.5 and 0.07. Maybe I'll plot this point, 1/2 and like 0.08. Do that. 0.08. So that's a very, very small value. Something like that. Okay. So we are concave up from 0 to 1. So this should be more cupish. And then concave down when in doubt, just move your point from 1 to infinity. And do the same thing on the left. So we are concave up from -1 to 0. So you have this cupish behavior, kind of like that. And then concave down from -1 all the way out to the rest of your graph. With that, kind of like that. So this is what you should be seeing. You're approaching the horizontal asymptotes, not touching them. You've got arrows on your graph. You've got a local minimum at 0, 0, and you've got the graph being concave up from -1 to 1 and concave down on the outsides. Okay, we're done. I'm 2 minutes over. I'm gonna send you an email with the homework I want you to do. I just want you to get started on some rational functions. You do have a quiz tomorrow. Expect it to be covering more of what we did in 4.4. I don't know how much curve sketching I could possibly ask you on a 15-minute quiz. So really just expect your quiz to focus on what we did in 4.4, talking about the second derivative test and concavity. Is the homework going to be due Friday? For curve sketching, no, because technically I'm finishing curve sketching over the weekend. So the curve sketching homework that I email you on, and I'll say this in the email, will be due Monday. Anything I assign tonight on 4.4 for the second derivative test, which there won't be much of, will be due Friday. It might be like 4 questions. Yeah, that is all. Okay. Anything else I need to address? All right, that's it. I'm gonna send you an email with the curve sketching homework. It'll be due Monday. I'll put up a couple questions for you to do using the second derivative test for Extrema. That will be due Friday, but that shouldn't be a big deal. And I'll post those office hour notes for you also. Yeah. You guys have a good night. I'll see you tomorrow.
You too. Thank you.
Bye, Burfin. Renee, I'm holding on for you if you wanna, you are waiting to.
Yeah, thank you.
Did you want to go into a breakout room? I don't know who's sometimes people hang on.
Yeah, sure, if you want to. I mean, yeah, I was just gonna wait till the recording stopped, so
Oh,
to talk to you. Yeah.
there we go. Thanks for the reminder.
Mhm.